Let's see if this is the right screen to be recording. The next one has E in it, right? And that's why I said, like, this is, like, in Unit 2 in this curriculum, we only worked with nice functions. But now we can really work with all of our functions. What rule do I need to do here to take the derivative? The product rule. And so if I was doing this, I'm going to think of 2x as the first function, and I'm going to think of e to the x as the second function. So when I take the derivative of 2x is 2, leave the e alone, plus 2x, and the derivative of e to the x is e to the x. But if we're talking about inflection points and concave up and concave down, we got to take the derivative again. So I'm just going to go again. Do I need the product rule for 2e to the x? No, because e to the x, like 2 is just a constant, a coefficient. So the derivative of 2e to the x is just 2e to the x. Do you agree with me on that? But now this is the product rule again, or it's what we just did. I feel like we did a very similar problem to this. The derivative of 2x is 2, and I leave the e to the x alone, plus I leave the 2x alone, and the derivative of e to the x is e to the x.
So theoretically, if you were to just keep doing derivatives, it would just go on and on and on.
Yeah, for e to the x, you would just keep getting a crazy, like this derivative is going to just keep getting longer because every time you're just going to keep getting a 2e to the x and then have the product rule again.
We can take out 2e to the x.
We definitely can. We could add this together first, but we don't have to, but I'm with you. We want to factor out what we can. They love to give you e to the x on the no calculator part, but I'm going to show you it just factors out every time. So if we factor out a 2e to the x, we will be left with 1 plus 1 plus x. You with me on that? 2e to the x. And so just x plus 2. When you can factor, and you're setting it equal to 0, you can set each part equal to 0. So you can set this 2e to the x equal to 0, and you can set your 2 plus x equal to 0. You would not have a calculator on this, so maybe you would have to do some work to figure out what happens here. But do you remember what e to the x looks like? Do you remember?
Is it the one that's just like a line?
Ooh, that's close. That's ln. It's just an exponential function, e to the x. It's just like this. So you went like this. It's like this. So maybe you don't remember what it looks like. If you were going to solve this, what would you have to do? Divide by 2, but we wouldn't take the square root. How would we get rid of e? We ln both sides, and we would get x equals ln of 0. Nope.
0.
Can you take the ln of 0? No. And so if you didn't know this, hopefully, like this doesn't work. This doesn't equal 0, which means if you ever have a problem and you can factor the e to the x out and equal 0, there's no answer to it. Because if you graph this, it looks like this. It has a horizontal asymptote. It never reaches 0. There's no number you could plug in there for x that would give you 0, right? Think about when we plug in negative numbers, we actually get fractions because the negative exponent isn't a negative number. And so don't stress about it. Just ignore it, okay? It doesn't equal 0. Which means after all of that, we did all this work, our only option for an inflection point is -2. So just like we did over there, I'm going to make my little chart, but I only have one number on it. And you could go back and you could plug it in all the way back up here, but I'm going to go over here. No matter what I plug into this part, is e to the x ever going to be negative? No, so that part's always positive. So I'm really just plugging in numbers into this, to this x plus 2, really, right? Because that's always positive. So think about it. If you plug -3 in here, -3 plus 2 is going to be a negative times a positive. If I plug in any number bigger than -2, I'm going to get a positive. So since it changed signs, we know x equals -2 is an inflection point. You with me on that? And just like for max and mins, if they ask you to justify your answer, You cannot just say x equals -2 and show me this work. You have to say f of x has an inflection point at x equals -2 because f double prime of x changes from negative to positive, or you could just say because f double prime of x changes signs. And this would be concave down, this would be concave up. Yes? So concave down from -infinity to -2 because f double prime of x is less than 0. And I can say concave up from -2 to infinity because f double prime of x is greater than 0. I feel like we just say the same thing over and over again, but I cannot tell you how many points you can get on the AP test for knowing this stuff. Because f double prime of x is greater than 0. And notice every time I'm saying f double prime. I'm not saying because the function. Okay? Oh my gosh, guys.
Where's your mic at?
Right here. Probably so she can't hear me. Alright, what's next? Oh my gosh, there's another one. Alright, we're going to do the derivatives on the next one, but we're not going to do it all out, so I can finish this up. We gotta wrap this up. Okay, so, what about this? Oh, very nice. That's already the first derivative. That's important to pay attention to. That we have the first derivative, so if we need to find points of inflection, we need to do the second derivative. Do you want to do the quotient rule, or do you want to bring it up into the chain rule? You love the quotient rule. Okay.
No, it's just because I hate the chain rule.
So quotient rule is derivative of the top times the bottom. That's just a constant on the top, which is why I would just do the chain rule. But that would be 0 times x squared minus 3, which means that's just going to be 0. Minus, I'm going to leave the 3 alone, and the derivative of the bottom is 2x all over the denominator squared. So if I simplify that, I get negative 6x over x squared minus 3 squared. Yeah. So if I want to find my points of inflection, I need to set the second derivative equal to 0 or where it's undefined, just like critical points. I think the fact that this is in the bottom, I think it's not going to be anything, but let's just think about it. If I just set this equal to 0, where does that equal 0? Does the denominator ever equal 0? If I was going to solve that, I could just multiply it over. So I just have negative 6x equals 0, or I get x equals 0. You with me on that? So don't let the fraction part throw you off. But the other part of this, and the part that we didn't do in the first introduction to increasing, decreasing stuff, is that if you have a fraction in your denominator for the first derivative or the second derivative, and you're looking for those possible max and mins in the first derivative or possible inflection points in the second derivative, you also have to look where it's undefined. And where it's undefined would be what makes the bottom equal to 0, which is really gross in this problem. But you have to think about setting this equal to 0. And is it okay if I just don't put the squared part, because I could just square 0 and like I could just take the square root of that and it just goes away? Which means if I solved this, I would get x squared equals 3, and I would get x equals plus or minus the square root of 3. So I really need to look at, on my number line, all of those values. I need to look at negative square root of 3, I need to look at 0, and I need to look at numbers on the positive square root of 3 side. Oops. I'm not sure what that was. Oh, just some spray for stinkiness. What's really great when I plug stuff back into this, look at this denominator. No matter what I plug into this denominator, do you agree that denominator is always going to be positive? Because it's something squared. So when I'm plugging numbers in, I'm really just plugging it into the top. So don't overthink this, okay? So if I plug in a number smaller than negative square root of 3, like negative 2, negative 6 times negative 2 would be a positive number. Yes? What if I plug in a number between 0 and negative square root of 3? Maybe you don't even know what negative square root of 3 is, but do you agree any number between 0 and that number is still a negative number? And if I take a negative number times negative 6, do you agree that that's still going to be a positive number? So that is not an inflection point. We checked it, but it didn't change, so that is not an inflection point. If I plug in a number bigger than 0, do you agree that's going to be a positive times a negative, which is a negative? And then a number after that, it's still going to be a negative. So this one, it doesn't turn out that that is anything, but it is something we have to look at. But this did change sign, so we can say x equals 0 is an inflection point. And this side's concave down, oh, this side's concave up, and this side's concave down. We're not going to write all that out because I'm tired of writing and I want to do other stuff. But we do want to check those, okay? And again, without a calculator, sometimes just think about what's happening, positives and negatives. I got one more quick thing to show you, and I'm going to show you this really quick because I don't think it's very useful. It's something I'm supposed to teach you, and maybe it works every now and again. But since we're talking about the second derivative, we can also talk about the second derivative test. The first derivative test is what we did yesterday. When we find the first derivative and we set it equal to 0, and we check the numbers to see if it changes from positive to negative or negative to positive, that's how we find maxes and mins, okay? That's how I'm going to go to always to find maxes and mins. But there is a way that you can do the second derivative to use the second derivative to find max and mins. And I want to write it out correct for you, so I'm going to get my paper, okay? Where's my big book of answers? I don't know. All right. Let me just walk around the lost forever.
The last puppy.
Oh, it's over here. Oh. So, the only time this is useful, in my opinion, is if the second derivative is really easy to find. Oftentimes, the second derivative is really gross. I don't want to do the quotient rule. I don't want to have a big mess. And so, if it's a polynomial, I guess that maybe I would do this. Well, I probably wouldn't, because how old is this book?
Yeah.
I don't know why.
We're like, did you do all of that?
No. I just want to write it out official. But I'm struggling. I'm almost there. I can tell. I can feel it. Okay. Oh man, there's a lot of words. Okay, there we go. Start writing. If f prime of x is equal to 0 or undefined at x equals a, then f of x has a possible relative max or min. That is not new information, hopefully. That's what we know is true. When we take the first derivative and we set it equal to 0, or where it's undefined, that could be a possible max or min. The first derivative test, we set the first derivative equal to 0, we make our number line, and we check positive, negative, negative, positive. But if you want to use the second derivative to do this, we could plug the value of a into the second derivative, and based on what we get, will tell us if it's a max or min. I'm going to show you this, and then we're going to practice one, and then we're going to be done with it. So, one option. If f double prime of a is greater than 0, then we know f of x is concave up at that point. So if we know it's a relative max or min, and we know it's concave up, I'll draw a picture here, then we can say that x equals a is a relative min on f of x. So if the second derivative at that critical point is less than 0, then we know f of x is concave down. And if it's concave down, think about that, at the possible max or min, if it's concave down, then x equals a is a relative max on f of x.
Mystics, and I hope you know that sometimes I don't know what I'm writing, but I'm just writing.
What's the third option that could happen? It could be greater than 0. It could be less than 0. This is why I'm not a fan of this rule, okay? Because the third option is, if we plug that point in and we get that it's equal to 0, then this test fails.
What?
And you need to go back to the first derivative test.
Are you serious?
I'm serious.
What's your head?
And so every now and again, people talk about conferences when I've been to that they're like, do we really need to teach a second derivative test because the first derivative test always works, and why would you ever want to do it? And they always talk about this one FRQ question, blah, blah, blah. I don't feel like I've ever seen a question that you couldn't do the first derivative test on. So just know this is there. Some people decide they like it. If it's a polynomial, you can do it. I'm going to have you do like 1 or 2 problems today with it, and then you're never going to be forced to use this test. Okay? It's true, it works, but I like the number chart. The line chart works just fine for me, so that's what I'm going to do most of the time. So let's do one example here, then I'll stop talking. Fine. And we're going to do the nice polynomial one, okay? So it says, use the second derivative test to locate and classify all x values of relative extrema. So the step 1, we still got to find the critical point. So we still got to use the first derivative, but then we can use the second derivative instead of the number line. And so you can see if you like this better. So step 1 is I'm going to take the derivative, and I'm going to get 4x cubed minus 12x squared. And the critical points come from the first derivative. So this is like what we did yesterday. I'm going to set that equal to 0, and I can factor out a 4x squared, which would leave me x minus 3. You agree with me on that? So I get x equals 0 and x equals 3. Those are my critical numbers. Now, if we were doing what we did yesterday, we could draw a number line, we can check positives and negatives. Yes, no?
So, wait, so the second derivative test, we only do the first derivative?
Nope, now, if we're going to use the second derivative test, I need the second derivative. But so even if I'm doing the second derivative test, my critical numbers still come from the first derivative. So what we did yesterday, like all of that still applies. If you're like, I'm never doing this, what you could do right now is you could do your number line, and you could figure out maxes and mins without doing this, but I at least want to show you it one time, and then you can never have to do it, okay? But this isn't a bad second derivative. If I take the derivative of that, I would get 12x squared minus 24x. You with me on that? And we don't have to factor this, but we're just trying to figure out if we get positives or negative numbers. So if it helps you, if you want to think about, you could factor out a 12x from that, and you'd have x minus 2. We are not setting this equal to 0 because that's to find inflection points. The second derivative test says you're going to take these critical numbers that you got, and you're going to plug them in and see what you get. But look what happens right away. If I plug 0 in here, what do I get?
0.
Which means I don't know what happens. And I got to go back to that other test over there. Oftentimes what it means is it's not a max or a min, but it doesn't mean that for sure. You really still have to go check. But I do want to say if we plug 3 in here, if I plug 3 in here, 12 times 3 is a positive, 3 minus 2 is a positive, which means I'm going to get a positive answer, which means that graph is concave up. So I can say x equals 3 is a relative minimum. Again, I've been teaching this class for a long time. I always show it to you, but by the time we get to the AP test and we're reviewing, I'm going to go back to this way if I think about it, but that's what you do. If we go back over here and we plug in a number less than 0, like -1, we're going to get a positive. -1 minus 3 is a negative, so that's going to be negative.
So the second derivative test is for the first derivative.
Yes, for the max and min stuff, which is also why I don't like it, because I feel like it's very easily confused.
It's just like a substitution for the line test.
Yes, it's like an alternative to the line test. I also don't like it because I like in your head that you think about first derivative as increasing and decreasing and max and min, and you think second derivative as concave up, concave down, and points of inflection, and that you don't intercross those, but this is like intermingling, right? If I plug 1 in here, I also get a positive times a negative. So we got 0 here. It was nothing, right? It didn't change signs, and that's usually what it means, but it's not always, and so you kind of have to go check that. And if you do plug in a number bigger than that, you're going to get a positive, which means you're going to get the same thing that we got. So just know, I want to show it to you. Today, when I ask you to do a problem, if you just do the line test, it's fine. I don't care. I'm never going to force you to do it this way, but I'm supposed to teach it to you, so I did. Okay, so let's look at these problems here.
Are we not doing 2?
We're not doing 2, because I'm tired of it.
So, are they going to ever ask us on a test to, like, solve this using
The
second derivative?
No, they're never going to tell you what to do on a question, and so that's why, yeah. So, we're going to skip number 1 on this one. I do want you to look at number 2 and number 3. And, yeah, let's do 4 and 5. I will say number 4 looks kind of gross, but that's already the first derivative. So, again, notice you need the second derivative. It's probably going to be gross.
Wait. What ones did you say for you?
Basically, we're just skipping number 1.
Can I cross it out?
You can cross it
So,
out.
wait, so we're doing every single one so far except 1.
Yeah, and then and you can cross out number 7, okay? So I think that's 5 problems to do. And we have about 15 minutes, so let's see where we get, and we'll decide what's going on from there. Actually, maybe let's go back and look at the first ones together, because they kind of make you think a little bit, but they don't have a lot of work. So let's look at the first page, and then I'll give you other ones to do. So that one says that that's the first derivative equals this, where the graph of f is increasing, decreasing, or reaching. Where is the graph increasing, decreasing, or reaching a relative max or min? Show your work and justify your answer. So they've already given you the first derivative. So if you want to find where it's increasing, decreasing, what do you need to do? Set equal to 0. And it's already factored for you, which means, can you tell me what the critical numbers are for this?
Yeah. 1, 2, 4.
1, 2, and 4, because if those are already factored for you, right? So sometimes you have to do a lot of work, and sometimes they just want you to check what's happening. But you could start with this knowing that your options for max and min and increasing, decreasing are 1, 2, and 4. And then you can plug some values in there. And I'm going to stop here, and I'm going to let you, I promise I'm going to be quiet. If you remember anything about what graphs look like, you might be able to tell me which one of these is not going to be a max or a min without even doing anything. Do you remember what it means if you have a 2 out here on the graph?
Wasn't it like or
Not just a b, but like we talked about the multiplicity, or it means a repeated root, about the x-axis. Okay, just do your thing. When it's a repeated value, it's never going to cross the x-axis. So like at that point, you can check to see whether it's positive or negative. But if you were going to graph this, it's either going to come up to 1 and then go back down, or it's going to come down like this. Because remember, like, even multiplicities don't cross, odd multiplicities do. And so, like, when you check this, this should be the same, whether it's positive, positive, or negative, positive. it should be the same value because of that. But you can plug it in, just kind of see what's happening on there, okay?